Dispatch decisions in energy systems are about deciding who supplies energy, when, and where. How do we make those decisions? Often markets are involved, but let's assume that we are in charge, as a central planner. This might actually be true for local energy systems like microgrids, or we can use this type of thinking to check whether markets work as well as we hope they do. Either way, we will need models to reason about such dispatch decisions in a quantitative way. Models for the costs and the emissions of various generators, and models for the constraints on their abilities. In this video, you will learn how the properties of individual generators relate to the overall objectives for decision-making in energy systems. I will also describe how the temporal constraints on power generators impact those decisions, and how energy storage can help alleviate those constraints. And finally, I will discuss how forecasts are critical to decision-making in the presence of those temporal constraints. One key differentiator between energy generation technologies is their cost. For energy system studies, we usually consider 4 cost categories. The first consists of the capital costs required to build a generating unit. Because generators come in many different sizes and their expected lifetimes can vary substantially, we usually report this as a cost per megawatt installed capacity per year. The second category is the operation and maintenance costs. This includes things like wear and tear, regular inspections and replacement, and the personnel and energy required to operate the plant itself. And the third and fourth are related to the energy production process itself. One is the cost of fuel, and the other the cost of carbon emissions, when that's applicable. Now, for modeling studies, we can simplify this picture a little bit by distinguishing fixed and variable costs. The fixed costs are incurred regardless of whether a generating is producing energy. This includes the capital costs and part of the operation and maintenance costs. It is expressed as a cost per megawatt per year. The variable cost consists of the fuel and carbon costs and the remaining part of the operation and maintenance costs, that part that is dependent on the amount of energy produced. Now, this is usually represented as a cost per unit of energy per megawatt hour often. Now, when you read energy system studies, you will also encounter an even simpler representation of costs. This levelized cost of energy combines the fixed and variable costs into a single number. But to do so, you have to assume the amount of energy produced by a generator in a year. And that way, you can convert the fixed costs to a cost per unit of energy and combine it with the variable costs. The levelized cost of energy, that we often summarize as LCOE, gives you a convenient single number to compare generation options. But relying on this number to plan the energy transition is risky, because in a complex and changing energy system, it's not obvious how much energy each unit will be asked to provide. So in this module, we will continue to use the fixed and variable cost model. Now, many different technologies are in use to generate energy, and the different properties of these units determine how they are best used and whether they should be used and installed at all. In this clip, I will illustrate the differences between generating units using generic examples. I focus on how the generators in the system contribute to the various system-level objectives for decision-making, which are cost, emissions, and reliability. For this, I will consider 4 types of contributions. And first we look at the costs, both the fixed and variable costs. In addition, we consider the emissions of pollutants, including greenhouse gases. And finally, the dependability of a generator, the ability to deliver power when it is required. So let's now consider 4 different classes of generating technologies and see how they score along these axes. First, we consider renewable energy sources, such as wind and solar power. Their fixed cost is substantial, but it has been decreasing rapidly in recent years. And moreover, once you've built them, the cost of generating energy is effectively zero. And there are no CO2 emissions to worry about. But the main concern with these energy sources is that their output is highly variable and to some extent unpredictable. So you cannot depend on these generators alone for a continuous supply of power. It's illustrative to compare this to traditional fossil generators. They generally have very low fixed costs and high reliability. But of course, as we all know, emissions are the problem for this category. In addition, the volatility of fuel prices means that the variable costs can be very difficult to predict. And of course, there are many efforts to reduce emissions from such fossil power plants, for example by equipping generators with carbon capture and storage technology. Such technology reduces the emissions but further increases both fixed and variable costs. And finally, we contrast these three options with power generation by nuclear fission. Nuclear generators have very large capital requirements, but produce energy relatively cheaply and dependably. They also don't emit harmful substances into the atmosphere, but of course there is the long-term problem of nuclear waste products to deal with. There are also practical risks associated with this technology. In recent years, we've seen capital costs of large nuclear generators escalate way beyond their initial estimates. And safety concerns have frequently led to lengthy shutdowns of older generators. So in order to make informed quantitative decisions about which type of generator to build and which to use, we require mathematical models for each kind of generator. And each of these aspects, costs, emissions, and dependability. But that is not enough. Some of the biggest challenges in decision-making for energy systems are related to the dynamic behavior of these units. In particular, two types of constraints play an essential role in driving dispatch decisions. First, we have limits to how quickly generators can adjust to changing demand. Generators can only increase or decrease their power output by so much in a given time frame. This is especially true for nuclear generators that are typically designed to run at a constant power level, so it's difficult to adjust them to follow daily demand cycles. A second limitation relates to the starting and stopping of generators. Often, especially for generators with complex thermal systems, there is a minimum on time and a minimum off time. And, in addition, a minimum notice period for starting up. You cannot simply instruct a nuclear generator or a large coal-fired power plant to run for an hour to cover the demand of electric ovens at dinner time. Moreover, in addition to these hard limitations, one should consider the cost involved with starting up and stopping a generator. Even if it's technically feasible, it may be economically unwise to do so. So keeping all this in mind, what is the challenge we face when determining an optimal dispatch for the system? Well, we have a variety of resources at our disposal to supply the energy demand, and we would like to find an optimal way to supply energy over a certain horizon, let's say one day. So to do so, we start with the total load we need to supply, which varies considerably over time. So how should we use our generators to supply that load? Well, the first part is easy. We have solar and wind generation, and because these sources are effectively zero cost and zero emission, we want to use them whenever we can. But, as you can see, this may not be enough to fully cover the consumption, and the remainder needs to be supplied using a combination of our other generators, fossil and nuclear. So keeping in mind these operational costs and the emissions, we'd like to use the nuclear units to supply as much energy as possible. but because of the limitation on their ramp rates and their minimum up and down time, we'd only use them to supply the constant baseload. And for the remainder, we'd ideally use the fossil plants with the lowest emissions and the highest fuel efficiency. Now, once we've used those to full capacity, we may need to fall back on less efficient fossil plants to cover the residual peak of demand. But this picture also illustrates a fundamental challenge in renewable energy systems. The presence of solar power generation can result in extremely low remaining demand during the midday hours, followed by a very steep ramp up to a high evening peak. Now, if you recall the ramp limits on generators, this might really impact your ability to use low-cost or low-emission sources of energy. So wouldn't it be nice if we could shift the energy production of solar panels to the evening instead of during the day? Well, this and more is what batteries and other forms of energy storage can do very effectively. They store the energy produced by renewable generators, allowing us to use it when it is most useful to us. And this changes the remaining demand that other generators must supply, meaning it is cheaper, more environmentally friendly, and more reliable to operate our system. So because of this ability, storage technologies are a critical component of a renewable energy system. They allow you to achieve a better trade-off between affordability, sustainability, and reliability. But as for the generators, if we want to quantify this impact, we'll need to specify a model for energy storage units. Now, in general, battery models can get really complex, but a simple model can be constructed by considering the following technical properties. Arguably, the most important parameter, and what makes it a battery in the first place, is the maximum amount of energy you can store inside. Next, we consider the charging and discharging of the battery. There's a maximum power that the battery can consume when it's charging, and a maximum power that the battery can deliver when it's discharging. And finally, when we are charging or discharging, there are losses. You can notice this by the battery getting warm to the touch, and this is represented by the charging and discharging efficiencies. And then I still haven't addressed the elephant in the room when discussing energy storage: the purchasing cost. So although the cost of large-scale energy storage, especially in the form of batteries, is still really high, it is coming down rapidly. The exploding use of batteries in electric vehicles is driving down costs to the point where battery storage is finding ever more use cases. And finally, I want to point out the importance of forecasts in decision-making involving generators and energy storage. To determine the best possible dispatch for this system, we need to deal with sharp changes in power requirements, for example, here in the late afternoon. So how should we optimally use the resources at our disposal to deal with this rapid variation? Well, recall one crucial complication are the RAM constraints of generators. They link what a generator can do in the future to what it is doing now. And that means we must consider what will happen in the future when we make decisions about the present time. That's done using forecasts. Forecasts of future energy demand and forecasts of future renewable energy production. In this example, based on our forecasts, we might choose to start ramping up our fossil generators early in the afternoon, because otherwise they may not be able to reach the desired output in time for the evening peak. This brings us to the end of this clip, in which I have shown you the main elements of modeling power generation in energy systems. Using 4 generic types of generating units, I have illustrated the different ways in which they impact the overall objectives of investment and dispatch decisions. This is done based on several objectives: costs, emissions, and reliability. And the costs can be represented in different ways, depending on the level of detail required. Next, I've shown how constraints on the ramping rates and on and off times influence the flexibility of individual generators, and therefore of the system as a whole. However, battery storage can help with alleviating these constraints, for instance by storing energy to use when the demand is highest. The necessity for doing so in a renewable-dominated energy system was illustrated using a typical daily power demand curve. Moreover, you've seen the importance of forecasting, especially when dealing with ramp constraints. It is essential to anticipate significant changes in demand and renewable generation so that you can dispatch other units or batteries on time. This way, we are well prepared to face the future.